Hey everybody, it's Miss Phoebus and I am back with a video on ancient Chinese mathematics. So the oldest math text that we have from China is the Yi, and it is the classic of changes. That's what it translates to. And this was written during the Zhou dynasty from 1050 BC to 256 BC. For mathematics, this book included a sophisticated use of hexagrams, or six broken or unbroken lines, and binary numbers. So if you look at the image that I have there, the one on the right, you should be able to see the image that was written on the tortoise from one of our other videos. Math was one of the six arts that students were required to master during the Zhou dynasty. They were expected to learn all six of them perfectly to be considered a perfect gentleman, or in the Chinese sense, a Renaissance man. And the six arts have their roots in Confucian philosophy. And so the arts are rites, music, archery, charioteering, calligraphy, and mathematics. Numbers, you start seeing them around 400 BC, and they were indicated with, at the beginning, small bamboo rods, and they had counting boards that a lot of times what I've been able to find is they were just drawn on the ground in the dirt, but there were, for people that had more wealthy, more money to spend, they were made out of bamboo, or even some fine cloths, and maybe even some marble. So there were counting boards that helped determine place value. So there were hundreds columns, tens columns, ones column. There was no zero, but they did use a space, which is very interesting. The zero didn't have its own character in a lot of places for a while, but they did just kind of leave it blank. With these rods, what they would do is they would indicate numbers in the position, in the place value system. And so we have 1, 2, 3, 4, 5. Those are pretty straightforward. Then 6, we move to a T shape. 7, 8, and 9 are also kind of an extension of that T shape. And then what they would do is they would alternate between writing the digits horizontal and vertical so that you could see and determine the place value. We have 2 here, and then there's a 9 here, a 3, a 5, and a 6, so that it becomes 65,392. And then here's one where there's nothing in the 10 space, so we have 2 ones, 3 hundreds, 4 thousands, and 6 10,000s to build 64,302. So that's where their numbers started. And these the numbers that are written there are like the counting rods. As we get into more modern mathematical number systems, here are their number systems that they use today. And if you notice, 1, 2, and 3 kind of look the same. 7 even maintains that T shape a little bit. And then they even pick up a new number for 10. And then, of course, look at 0. 0 is a very intricate number. Almost looks like a smiley face in there, though. So the number system has changed since the beginning. But the counting rods were the original reason why that they wrote them this way. Li Hui was a mathematician renowned in ancient China for approximating pi. He solved all the problems in the book, the 9 chapters of the mathematical art, and he wrote his own book, Sea Island Mathematical Manual, in 263. Originally known as the 10th chapter, or the commentary on the 9 chapters, that's what his book is known as. It was re-edited and solely published as an independent book during the Tang Dynasty. The most influential math text in China is the Nine Chapters on the Mathematical Art. It's one of the earliest written ancient Chinese mathematic books and is still around. The math problems are on measuring and architecture, engineering, and surveying, and they included information on several generations of mathematicians ranging from 10th century to 2nd century BC. So a lot of the older mathematicians, their work still survives in this Nine Chapters of the Mathematical Art. Liu's major contributions were algebraic number theory. So he was really big into simplifying fractions, looking at square roots being irrational, decimal approximation of square roots, rewriting the definition of the word ratio, and proving the Pythagorean theorem. So again, we are dealing with the Pythagorean theorem way before Pythagoras. He was also into spatial geometry, including areas and volumes. He had an approximation for pi to help him calculate the area of a hexagon, a decagon, a 24gon, all the way out to a 3092gon. Pi, his approximation was 3,927 divided by 1,250, which is approximately 3.1416, and it was named after him as the Hui ratio. And he found that the formula for a sphere in the 9 chapters was wrong and fixed it. The history of Chinese math and mathematicians was mostly lost or destroyed over the centuries. For example, the despotic emperor Shi Huangdi of the Qin dynasty ordered the burning of all books in 213 BC. Scholars in the following Han period had to transcribe China's literary and scientific traditions from memory or whatever remained of the scroll fragments they pieced together. That's sad. Knowledge of astronomy and other areas was often handed down from father to son, and only later was it recorded in texts. Unfortunately, very few texts dedicated to a mathematical astronomy have survived. Since the 16th century, Chinese math history has also been denied and ignored by the Western dominance of science and technology, both inside and outside of China. So the idea that China didn't participate in math or have any part in the development of math still goes on today. But Europe was not the only one, and Europe was still in the Dark Ages most of the time until this point. So, I mean, Chinese history just, being denied and ignored is pretty terrible. They had quite a contribution there. There are several existing Chinese applied mathematics texts, which are a collection of problems and solutions organized in chapters according to their practical applications. These texts prove that the Chinese were the first society to use some of the most basic and advanced mathematical principles and concepts utilized in modern times. The Chao Pei is a book that translates into the arithmetic classic of the Gammon and Circular Paths of Heaven. That's the full name of it. It was written before the 3rd century BC. It has problems about fractions and using a common denominator, proofs of many geometric theories, including the Pythagorean theorem, and an accurate process of division for finding out the square roots of numbers. The Chao Pei also presents the oldest known proof of the right-angled triangle theory, called the Husan-Hu diagram. This theory, commonly known as the Pythagorean theorem, shows that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse, where a squared plus b squared equals c squared. And you can kind of see the right triangle right through here. And so all of this is proof that the Pythagorean theorem works. All right, so the origins of mathematical matrices lie with a study of systems of simultaneous linear equations. So the 9 chapters of the mathematical art gives the first known example of the use of matrix methods to solve simultaneous equations. And what that is these are like 2 lines or more on a single plane. Where do they cross? Where do they intersect? So today they are not simply used for solving systems, but they are also used for describing quantum mechanics of atomic structure, designing computer game graphics, analyzing relationships, even plotting complicated dance steps. So they are used in lots and lots of places. So what we're going to do is we're going to study some matrices. So matrices is the plural of matrix. And so what we're going to do is we're going to look at size as well as adding and subtracting. And then in the next video, we'll look at some multiplying matrices. We don't divide matrices at all. So matrices are often referred to by their size. The dimensions for a matrix are the number of rows times or by the number of columns, rather than the width and length. For example, consider our following matrix, matrix A. If we were going to list the size of this matrix, we would count rows. Rows go left to right. So we have 1, 2, 3 rows. By columns, 1, 2, 3, 4 columns. So this is a 3 by 4 matrix. That's the size of it. And 3 times 4 is 12, and there are 12 elements inside this matrix. And an element is just a number inside that matrix. It doesn't have to be a number, it could be a variable. All right, so I need you to really quickly jot down on a sheet of paper what the size of matrix 1 and 2 are. All right, so matrix 1, let's count the number of rows. We have 1, 2, 3 rows. We have 1, 2, 3 columns. So 3 rows by 3 columns. It's a 3 by 3 matrix. How about number 2? We have 2 rows, 3 columns. So this is a 2 by 3 matrix. Now you don't want to switch those numbers up, because you switch them up, then you say, hey, we have 3 rows, and we don't have 3 rows in number 2. So make sure you keep it rows by columns. Okay, so matrix elements, the numbers or variables or expressions contained in a matrix are called its elements. So here is matrix A. Matrices are always named with capital letters. If you notice over here, we have these little a's. Little a's refer to matrix A, but they are attributed to the elements, the things inside matrix A. You see these little numbers? There's a sub 13, a sub 32, a sub 23, a sub 33. So what these little numbers are is they're designations where to look within matrix A to find a particular number. And remember, it's always rows then columns. So this one is telling us to go to row 1, column 3, and then state what number is there. So row 1 is here. This is column 1, 2, 3. Row 1, column 3, 3 is the element. This one says go to row 3, column 2. So row 3, 1, 2, 3, column 2. 1, 2. There's my element, 8. All right, why don't you try the last 2? All right, this one says row 2, column 3. So row 2, column 3 is 6. And then this one, last one says row 3, column 3. Row 3, 1, 2, 3. We've got a 9. So this little notation is actually sometimes used on the ACT, but it's a little notation that helps you find the pieces inside the matrix if they want to know what's in there. So I want you to try. These 2 are for matrix B right here, and these 2 are for matrix C right here. All right, let's look at matrix B. We're looking at row 2, column 2. So row 2 is here, column 2 is here, and those line up with a -2. All right, let's look at 3, 1. So that's row 3, column 1. Those two arrows are pointing to 9. All right, number 4, row 2, column 4. So here's row 2, here's column 4. They intersect at 8. This one is looking for row 3, column 3. 11 is your answer. How'd you do? All right. Matrix arithmetic. Most of the time, in order for matrix arithmetic to occur, the matrices need to be equal or the same size. So here, matrix A is a 2 by 2. Matrix B is a 2 by 3. I couldn't add or subtract matrix A and B together. Matrix C is a 3 by 2. Again, doesn't match any of the ones so far. Matrix D is a 2 by 3. So I could do something with matrix D and matrix B. I could add them, I could subtract them because they are the same size. But everything else, I can't do anything with because they're not the same size. Now, there is an exception with matrix multiplication. We will talk about that in the next video. But addition, subtraction, you have to have them being the same size. All right, so we're going to look at equivalent matrices. The following matrices are equivalent. Find the value of the variables. So here's matrix A. It has all kinds of nice numbers inside, but look at matrix B. Do you see how there's variables? So what we're going to do is, because these matrices are equal to each other, we can even set them equal to each other. They've told us that they are equivalent. 1 is equal to, and they're the same size, so this works. 6, y plus 4, z divided by 3, and 1. So if you notice, the number components, 0, 0, 6, 6, they're equal, 1, 1. So if we had different numbers in those spots, then it wouldn't be equal. So because those are equal, then I can say, well then, let's see if I switch colors. 4 equals x. Let's see here. -2 equals y plus 4. And we could solve for y. Solve for y, subtract 4. You get -6 equals y. 3 equals z divided by 3. So to get rid of divide by 3, multiply both sides by 3. And you get 9 equals z. So you can figure out those variable values with a little bit of arithmetic. All right, so here's number 5. I want you to figure out what the value of the variables are. Pause the video so you can work that out. All right, let's look at these. So because we know our matrices are equal to each other, A plus 12 will equal 18. 2B will equal -14. 23 is going to equal A plus C. Now there's two variables there, so we may need to wait a moment. And D equals 3B. So there's two variables there. So for the first row in that left matrix, we could figure out what A and B are, and then we can use that to help us figure out what C and D are. So if I would subtract 12, A equals 6. So for B, I would divide by 2. So B equals -7. All right, for the next one, 23 equals, we already know A is 6 plus C. So we would subtract 6. So 17 equals C. And we already know B. So D equals 3 times negative 7. So D equals negative 21. All right, now to add the matrices, remember they have to be the same size. And what they will do is they will create a matrix of the same size. So what I like to do, you have these little bars here to show that it's a matrix. I know that these are both 2 by 3s, so I'm going to fill in some blanks and make a 2 by 3 answer. And now it's ready to receive the sums, the addition. And so what I'm going to do is I'm going to add the pieces that are in the same spots. So top left corner plus top left corner goes in the top left corner. So 1 plus 6 is 7. Top middle piece plus top middle piece will go in the top middle piece. So 3 plus negative 3 is 0. 4 plus 11 is 15. I want you to do row 2. See if you can figure out what row 2 looks like. Negative 7 plus 0 is negative 7. 0 plus 5 is 5. 5 plus negative 4 is 1. There you go. It's really easy if you know what pieces go where, and especially if you have a place to set it up. You're not just randomly building the matrix as you go. So why don't you try this one? It's another 2 by 3 plus 2 by 3, so we're going to get a 2 by 3 answer. I'm going to set this up. Negative 5 plus negative 3 is negative 8. 8 plus negative 4 is 4. Negative 9 plus 0 is negative 9. 7 plus 8 is 15. 0 plus 6 is 6. 12 plus negative 5 is 7. So, adding matrices. Not too bad. I don't think. Just add numbers. Alright, so I want you to try 6 and 7. And yes, you can add them because they are the same size. It's 6, and then they're the same size as 7. Alright, so the answer for matrix 6 is a 2 by 2. 4 plus 7 is 11. 5 plus 3 is 8. 1 plus negative 5 is negative 4. Negative 2 plus 4 is 2. Matrix for number 7, we've got a 3 by 2. All right, so 3 plus 4 is 7. 2 plus 3 is 5. 2 plus 5 is 7. 4 plus 1 is 5. 6 plus 6 is 12. That's different. 5 plus 4 is 9. There you go. Did you do okay adding? Now, in addition of matrices, just like in regular addition, order doesn't matter. So, in subtraction, order matters. So the one on the left is definitely the one that you start with, and you're subtracting the one on the right. So subtracting matrices, this is a 4 by 1 minus a 4 by 1. We will create a 4 by 1. We'll just subtract. Negative 2 minus 7 is negative 9. 0 minus negative 8 is 8. 3 minus 0 is 3. 6 minus 4 is 2. So subtraction is the same way. They have to have the same size matrices in order to be subtracted. All right, so why don't you try 8 and 9. Pause the video. Okay, so number 8, you're going to have a 2 by 2 answer because we have a 2 by 2 subtracting a 2 by 2. So we got 3 minus 0, that's 3. Negative 6 minus negative 2 is negative 4. 4 minus negative 4 is 8. Negative 7 minus 6 is negative 13. Number 9, we have a 3 by 2. So 4 minus negative 8 is 12. Negative 7 minus negative 1 is negative 6. Negative 6 minus 3 is negative 9. 2 minus 2 is 0. 3 minus 1 is 2. 0 minus negative 5 is 5. So scalar multiplication is almost like the distributive property, except we're going to multiply the number on the outside, the scalar, times every value inside, and we're going to create a new matrix. Now that new matrix is going to be of the same size as our original matrix. So our original matrix is a 2 by 3, and all we're going to do is we're going to take that 4 and we're going to multiply it times every element. So 4 times 3 is 12, 4 times 2 is 8, negative 10, 32, negative 12, and 4. And so we have just multiplied everything by a scalar. Scalar is just a real number. It can be positive or negative, it can be a fraction, decimal, it can be 0. All right, so sometimes what they'll do is they'll set up the scalar multiplication and ask you to, to do something just based off of the letter, so you have to match the letter to the matrix that's already there. So they want us to take matrix A and multiply it by 5, all the elements by 5, and then they want us to take matrix B and multiply it times negative 3. And really what we've done is we have renamed. Our new matrix is going to be a matrix where everything's been multiplied by 5. Our new matrix over here is going to be that matrix, everything multiplied by negative 3. So we're going to have a 3 by 5. And you do need those brackets there. Make sure when you're done you've got your brackets and everything's lined up nice. So 5 times 5 is 25, 5 times 2 is 10, 5 times 7 is 35, 5 times 0, 5 times 1, 5 times negative 3, 5 times 1, 5 times 10, 5 times 2, 5 times 9, 5 times 8, 5 times negative 2, 5 times 0, 5 times 1, 5 times negative 3. So just multiply everybody in that matrix by 5. Over here, we're multiplying everybody by negative 3. Alright, so let's try this. Multiply by negative 3. So 1 times negative 3 is negative 3. Negative 12. 6. Negative 18. And 3. Oh, there's another 3. There's another 3. That's going to be what? 12. Negative 60. Negative 27. 6. 6. 21. Negative 27. Negative 15. Make sure you're multiplying by the right number. Alright, so here you go. I want you to do 10 and 11. Alright, number 10. We're going to multiply everything by 3. We're going to end up with a 2 by 3. So we're going to have 3, 6, 9, 12, 15, 18. Alright, number 11, they want us to multiply everything by 1/2. Now you could write it as a fraction or a decimal or even a mixed number. I'm going to recommend decimals. So we're going to have 5 times 1/2 is 2.5. 2 times 1/2 is 1. 11 times a half is 5.5. 9 times a half is 4.5. 4 times a half is 2. 14 times a half is 7. Alright, so that's it for the beginning part of matrices. I'll see you in the next video where we're going to multiply matrices. Bye!